Welcome back. All right, today this time we're going to be talking about line integrals. Excuse me. Wow. Now on screen here you have this definition for these line integrals that says, let C be a smooth plane curve defined by the parametric equations h of t and g of t, where they're going to be x and y respectively on the parameterization for the vector field function. All right, and that's given by this right here. And we want to make sure that we bound our t values between a and b. That way we can find what different parameter values we're going to be looking at. Now we want this curve to be smooth, and it's going to be smooth if the derivative of this position function is going to be continuous and if it's not equal to 0 for all of the t within the domain. The line integral, this is where we get into the definition for the line integral. So the line integral of this function along that curve is going to be denoted in this fashion. And you're going to see we have an integral. It's not a definite integral here because we have some sort of curve that we're integrating, and it's not an indefinite, right? So we need to figure out what bounds we have for this curve to make sure that we make this a definite integral. And we're going to do this for the integrand of the function. So that's what we're integrating is the function. And we're going to do this with respect to s, where s is going to be the arc length of that curve. All right. Now, if we recall back from Calc 2, in Calc 2, we had this definition that we were able to extract and we were able to derive for the arc length of a function. And this was the arc length of a function, and so it was just the integral from a to b, and that's again from the 2x coordinates that we were looking at, with respect to ds. All right, this could have been thought of as the t coordinates being bounded, very similar to here, where ds is just this piece here. But one of the things that we then want to observe is that as we start looking at this line integral, the line integral for the curve of this function f of xy with respect to the arc length, if we make our substitutions for our parameters like we have them defined up here, we can do this to say this is going to be the integral from a to b. And again, because we're integrating with respect to some curve, that curve is bounded between a and b, so here we are, a and b. Now our function no longer has the x input because that x input is now h of t. The y input is now g of t because again we're parameterizing this curve. ds, we got to be careful with ds here. ds is this given piece here. But this given piece kind of looks very, very familiar to us because this is just based off of r of t. Would you agree that ds here is just some sort of magnitude of r of t? Well, sure. So what I'm going to do here is I'm going to say, okay, well, we can derive that ds is just going to be the magnitude of r of t, or sorry, magnitude of r prime of t. My apologies. Magnitude of r prime of t. And then this is going to be dt. The ds portion here is this whole piece right in here. All right, so this is how we're working with line integrals. This is the notation, and this is what we want to observe. So here's going to be a question. Here goes this example. We want to evaluate the line integral over the curve xy to the fourth, and this is going to be ds, where the curve is the right half of the circle, and we're going to say x squared plus y squared is equal to 1. And this is going to be rotated in the counter counterclockwise direction. Alright, so we now want to figure this out. Alright, so here we go. And actually, you know what? I'm going to make a quick change. I had a quick change of heart. What I'm going to do is I'm going to make this x squared plus y squared is equal to 4. That way this can have a radius of 2. Alright, perfect. So this is what we want to look at. We want to evaluate this line integral that's given to us here, where the curve that we're going to be integrating over is just the right half of this circle, and we're going to make sure that the curve is being traversed in a counterclockwise direction. Alright, so the first thing that I want to do then is I want to start by graphing this particular curve so that I can see kind of what my domain is in a sort of sense. Alright, now they said right half, so that means I kind of only want to focus on the right half of the circle. There we are. So here's my y, here's my x. There we are. Alright, so that's 2, -2, and 2. Alright, so I want to make sure I graph this. Alright, so there's the right half of the circle, and again, we're going to be making sure that we rotate counterclockwise. So counterclockwise is going to move in this direction. Alright, perfect. So once we have this, then we're going to be able to start working with this. Now, one of the things that I want to look at then is using this line integral. Notice that the line integral that I was given in this piece right here, that line integral kind of fits this stipulation. What I want to do then is I want to move it into this type of parametrization. I want to make sure that whatever x and y coordinates I fix, they're going to be fixed on this particular circle. So let's go ahead and let's then parameterize, and I'm going to say parameterize the curve, or in this case, the circle. So that's our first job. We need to parameterize the circle. So let's go through and let's parameterize the circle. The x coordinates, well, this is a radius 2, so I could say this could be something like 2 cosine of t, and I'm going to say y is equal to 2 sine of t. Now take a minute and see if that will generate the equation of a circle, right? If we square both of these results, square this, that's 4 cosine squared, square this, that's going to be 4 sine squared, add them together, and we just get 4, which means it parameterizes that circle. Does it move this in a counterclockwise direction? Well, as your t values increase, meaning as these t values get larger, do they move in a counterclockwise direction? And they do, because this kind of resembles that unit circle. All right, so it's looking good so far. Now what I'm going to do is I'm going to define this as my vector. This is 2 cosine t, and this is 2 sine t, which means all I need to do now is take a derivative here, which will get me -2 sine t and 2 cosine t. There we are. And the reason I want to take a derivative of this parametrization is because this individual piece right up here says that I need the magnitude of the derivative of that position function. So let's go ahead and let's take the magnitude at this time. Here we are. Square this, and it should just be 2. All right. And again, when you square this individual piece, you get 4 sine squared t. Square this piece, you get 4 cosine squared t. Add them together, you should be able to factor out a 4. And then you have sine squared plus cosine squared multiplying that, and that's just 1 because of the Pythagorean identity. Square root of 4 is just 2. So there we are. All right, awesome. It's looking really good so far now. So far now we have this dt, we have this this magnitude of the derivative. All I need to do now is make my substitutions. All right, so this line integral that we're looking at for this curve of xy to the 4th ds, this is now going to be the integral, well, the integral for what t values? The t values here begin at negative pi halves, and they start traversing in this direction over to pi halves, which means this line integral, at least for the curve, is bounded between negative pi halves and pi halves. The substitutions that we're going to make, my x-coordinate, I define my x-coordinate as 2 cosine t. My y-coordinate, I defined it as 2 sine t, and that's to the 4th. And then magnitude, that magnitude was 2. And then I have that dt. All right, perfect. So I'm going to go ahead and illustrate what we had here so far. So this in here was that x of t. This in here was that y of t. This right here was that magnitude of r prime of t. And then that's just, well, the dt. Perfect. So what we're going to do is we're going to work with a u substitution here. All right, to make things a little bit easier here. So let's see, I'm actually not going to make things too easier here because we have a 2, we have a 2 to the 4th, and we have a 2. So it's going to be 2 to the 4th, 5, 6, so it's going to be 2 to the 6. So I have 2 to the 6, and that's going to be integrated from negative pi halves to pi halves. And that's going to be cosine of t multiplied by sine to the 4th t dt. Now, I think a u substitution will work just fine right here. So I'm going to go ahead and make that u sub. So I'm going to say u is just equal to sine of t. That means du will be cosine of t dt. All right, so that's 2 to the 6 integral. So cosine of t right there, cosine dt should be du. Sine of the 4th, that's just going to be u, so that's in here looking like it's u to the power of 4, and then that's just du. Changing our limits of integration. All right, so let's check those limits of integration. I need sine at negative pi halves. So sine in this particular piece, this is my substitution that I'm making. So negative pi halves for sine. All right, so we need to look at sine in here. So x component is 0, down to y component, that's just going to be 1. Or sorry, negative 1. So this here is negative 1. And then making our top component, all right, so this was sine at negative pi halves is negative 1. And then sine at pi halves, that's our upper limit right here. So sine of pi halves, that should just be 1. There we are. Perfect. All right, we could just go with that integral. And that's going to be 2 to the 6 multiplied by u to the power of 5 divided by 5. And that's going to be evaluated from negative 1 to 1. So that's 2 to the 6 multiplied by, that's going to be 1/5 minus another minus. So it's going to be plus 1/5. And that's going to give us another 2, so that's going to be 2 to the power of 7 divided by 5. Now we can go through here, 2 to the power of 7, then that's going to be divided by 5, so that's going to be 128 over 5 as our final answer. There we are. Nice. And that's the line integral that we want to look at. Now, some of you guys might be thinking, well, what does this line integral really talk to me about, right? Well, let's go ahead and let's get that visualization going on GeoGebra. So follow me along to the GeoGebra classroom. All right, here we are. And what I'm going to do is I'm going to go down here to this line integral example, and I'm going to click on that. And here's the line integral example. Now, this line integral example, what I did was I embedded that feature for that xy to the fourth divided by 2. All right, so that kind of looks like the function that we're working with, all right, just not quite. But the curve is what we want, right? This curve is the curve that is actually on, oops, let's go this way, sorry. The curve is actually what is on the right-hand side. So as you see, this curve is actually creating a curtain type of a feature. And that's what the line integral is. The line integral basically calculates the integral of this surface along that curve. In other words, it creates that area that we then observe. So when we talk about line integrals, this is what we're doing here. All right, nice. So again, this is on GeoGebra for the classroom, so you can go ahead and look at it there. Again, I just embedded this curve on this actual surface, and then I made it show this line integral as it keeps on sweeping through that integration. All right, so let's go back to the classroom and we'll go ahead and move on from the examples. All right, so now that we're back, let's go ahead and let's start looking at these line integrals a little bit more deeply. Now, say that the line integral isn't a smooth curve when we started, right? So what I want to do here is then I want to start analyzing. What if we had a curve that looked like this, like such, where this whole curve is split up into three different curves. Call it curve 1, call it curve 2, and then call it curve 3. Then I could say that when I'm looking at some line integral for this function over this curve ds, then I can do this line integral, because it's not smooth, I can break it off into different pieces. So I can break it off into different pieces. The first line integral is going to go over curve 1, and that's still going to be using the function with respect to its arc length here. Plus, we can again do this with respect to the second curve, f of xy ds, and then plus the third curve, and in here we're going to have ds. There we are. And again, this is where the original curve is made up of C1 union C2, union C3. So the original curve that we're observing is made up of different curve components, and again, we can go ahead and evaluate that using those different curve components, which is going to be really good for us. All right, now, next example. We're going to see how this is going to play out on kind of like a grander scale. So we want to evaluate the integral over the curve for the function 4x cubed ds, where the curve C is the curve shown below. And I will go ahead and draw that in just a little bit, so you'll see it pop up on your screen. All right, so here's the curve. So the curve C is the curve made up by all these three different curves. Curve 1 is given by y is equal to -1. Curve 2 is given by x cubed minus 1. Curve 3 is given by x is equal to 1. So in this type of problem, you can expect to see this type of problem on your next exam, which I will give you some type of integral that I want you to evaluate, and then you're going to have to go through and you're going to have to then figure out what are the parametrizations that we need for this curve. All right, so that's the first thing that you need, is that we need to parametrize all the curves. So that's the first thing that we need. All right, so that's exactly what we're going to do. So I'm going to go over to curve 1. All right, so curve 1. And you know what? I'm going to do this all in different colors. That way you can follow along with the different parametrizations that we're doing for all these curves. So here we go, curve 1. So curve 1 here, notice that every single ordered pair here contains a y value of -1, which means if we want to build this parametrization, then all of our ordered pairs, or all of these vectors that we produce, will have a y component of -1. The x component is really the only component that's changing, which means for our x values, it's just going to be the t component. That's going to be what's changing. Now, what do we want this to change between? Well, the t values are corresponding with the x values, and the x values only go between -2 and 0, which means that we're left with this function, r of t, to just be t comma -1. And this is going to be for t being bounded between -2 and 0. Nice. Now, trying to think ahead, well, if we parametrized it, then we're naturally going to need a derivative as well. So let's go ahead and let's find the derivative of this function. That way we can find its magnitude. All right, that's going to be 1. That's going to be 0. So then the magnitude is just going to be 1. Not too bad. All right, let's keep going. Let's go to curve 2. All right, here we go, curve 2. So curve number 2. Curve number 2, our x-coordinates and y-coordinates are both changing. So we can see here from this function that y changes with respect to x. So if we naturally just let x be t, then our y-coordinate will then automatically just become t cubed minus 1. Under these assumptions, r of t is now going to be t comma t cubed minus 1. We now need to figure out what t components we need to go through. So the t components, let's see, I need this vector or this point to come out and this point to be the last point. Alright, so let's go through. X is equal to t. Awesome. Y is equal to t cubed. Great. So let's see, if t is equal to 0, 0 and 0, that becomes 0 and -1. That's a starting point. Nice. And as we increase, let's see if I could do this. Here we go. So if t is 1. So if t is 1, that means this vector is 1, 0. 1, 0 is this component, which means it goes between 0 and 1. Nice. Let's take the derivative. This is going to be 1. This is 2, or excuse me. This is 3t squared. There we are. Take the magnitude. The magnitude here is going to be 1 plus 9 t to the 4th. Like such. Excuse me. Alright, good so far. Let's look at another one then. Alright, I already got orange, I don't want to do red, so let's do this in gold. I haven't done anything in gold yet. Alright, so let's go with curve 3. Alright, I'm going to do curve 3 right under here. So let's see, curve 3. So curve 3, that was that x is equal to 1. And again, all of these ordered pairs here have the same x component, which means x is going to be equal to 1. Parametrization-wise, that means that your y values are the ones that are changing, and they're just changing with respect to t. Nice. So once I have this, and I can just say, well, my r of t component is just going to be 1 and t. And then I can just say that this is going to be 4. And let's find out what t values we need. So the t values are the y values, and the y values just go from 0 to 2. It's looking good so far. Take the derivative. So that's 0, that's 1. Take the magnitude. Should just be 1. Perfect. So, now that we have all the parameterizations set, we can now talk about going through this whole process to figure out what is that line integral for the curve. So let's go through the line integral for the curve 4x cubed ds. Well, that's going to be split up into 3 line integrals. All right, the first line integral is going to be c1, and that's going to be 4x cubed ds. Then we're going to go curve 2. That's going to be again 4x cubed ds. And then we're going to go with curve 3, and once again that's 4x cubed ds. And all we're going to do is make our substitutions in here to make sure that we elaborate what we're working with. So my first line integral was curve 1, but curve 1 is bounded between -2 and 0. So for curve 1, this goes between -2 and 0 for my t values. My function is 4 times x. The x component is just t for that specific example here, and that's going to be t cubed. ds, again, that's going to be the magnitude. So that's going to be a 1. That's my magnitude times dt. There we are. Perfect. So that's my first integral. That's the integral for curve 1. Let's go for the integral on curve 2. The integral on curve 2, here we go. That's going to go from t is equal to 0 to t is equal to 1. And that's going to be 4 times the t component. My t component here, or sorry, my x component. My x component for curve 2 is just t. So that's t to the power of 3 multiplied by this piece here, which is square root of 1 plus 9t to the 4th. Nice. Multiplied by dt. All right, because again, that was a magnitude. Plus third integral, curve 3, that goes from 0 to 2. So that goes from 0 to 2. And then again, we still have 4 times, this is going to be the x component, where my x component here is just 1. So that's just x component of 1. Nice. That's going to be cubed. Magnitude. The magnitude here looks like it's just 1. And then we just multiply by dt. There we are. So this is our line integral. The two outermost integrals are the easiest to work with. The innermost, the middle term here, is going to be one of the harder ones to work with, but it's not going to be too bad because we can just use a u substitution. All right, so we can go through and we can set this up. Let's go ahead and let's clean this up just a little bit more. That way we can start evaluating this. All right, so I'm going to factor out a 4 here. So it's going to be 4 multiplied by -2, 0, and this is just going to be t cubed dt, plus, once again, factor out a 4, and this goes from 0 to 1, and this is going to be t cubed multiplied by the square root of 1 plus 9t to the 4th, dt, plus 4 times the integral from 0 to 2, and that's just going to be 1 dt. All right. So from here, I want you all to then just finish the problem. So keep going. All right. So when you keep going, you will be able to get this approximation here, which will be negative 5.732 as your answer. All right, so again, the middlemost term, you use a u substitution, u for the radicand, and the two outer integrals would just be a direct integration. Awesome. So that wraps up this example. Now, I want to illustrate a few more examples before we move on as to how we keep using these specific line integrals. All right, so I'm going to give you guys a few, about 2 more examples before we move on from this section. All right, so let's try to get this example going once again. And we still want the exact same process to happen over again for the same function. So what I'm going to do here is I'm going to cut this function out and just paste it. There we go. All right, now I want to copy this. There we are. And I want to copy it here. Paste. Oh, look at that, perfect. All right, now the only difference here, and I'm going to change some of this stuff around. The only difference for this example, even though we're working with similar curves, where C is the line segment from -2, -1 to 1, 2. All right, so the line segment in question now is going to be the one that goes from -2, -1, so -2 down to -1 over to 1 up at 2 up this side, which means the line segment in question is going to be this here. All right, this is a line segment. Now, it's saying that the line segment is actually moving from this point, so it's moving from -2, -1 over to that point. And again, we have to give this orientation. All right, so we have to make sure that we get an orientation for the curve, and currently the curve is moving in this direction. All right, so the first thing that we need to do is we need to parameterize the curve. So we're going to go with the parameterization of the curve. All right, what I'm going to do is I'm going to shoot a vector, or I'm going to make this a vector, and I'm going to move this vector, or I'm going to describe this vector as a vector that originates from this original point, -2, -1, and extends all the way to that point. So in order for me to get that vector, I'm just going to say we're going to move from this point to that point, so I'm going to call this P, and I'm going to call this Q, and we're going to grab vector PQ. Here we are. All right, ending minus beginning. All right, so the x-coordinates, ending, we end here, ending minus beginning. So 1 minus -2, that's going to be 3. Ending minus beginning, that's going to be 3. So here we get the vector just to be 3, 3. Awesome. Now the starting point, or the starting vector that we then want to observe, is this vector here that we shoot out towards the very beginning, or that initial point. So I'm going to say point P is the one that we want at -2, -1, and that means that our vector that's going to grab the position, if you remember back from chapter 12, all we need is a point and a directional vector. We have the point, we have the directional vector. All right, here we go. So the point starts at -2. So this is going to be -2 plus 3t. And then it's going to be -1 plus 3t. Again, the direction, and the point that it starts at. Awesome. So we have this vector. Let's find the bounds for this parameter. So the bounds for this parameter, let's see, the t-values must be able to generate the ending points that we need. So it must generate this point and this point. So in that sense, let's see what happens if we start at 0. So if t is equal to 0, we get -2, -1, which is the initial point. If t is 1, then this coordinate here, if t is 1, it's going to be 1. If this is 1, then it's going to be 2, which naturally ends at the point that we need. So that's looking real good then. Let's take the derivative. That's just going to be 3, and that's 3. And let's go ahead and take the magnitude of this. Nine plus 9, that's going to be 18. Square root of 18. That's just 9 times 2, so that's going to be 3 root 2. There we are. Perfect. Alright, so let's go ahead and let's start evaluating this line integral then. Now, the line integral over the curve, which is 4x cubed ds, for that curve given from that point, is going to be, by the parametrization that we took, it's going to go from 0 to 1, 4 times x cubed. X, what was that x component that we were looking at? That x component that we were looking at here is this piece. That is just, I'm going to write this in this color, -2 plus 3t. There we are, and that's going to be to the power of 3. Magnitude is 3 root 2, and then this is just going to be dt. There we are. So we have a lot of constants. We can factor out a lot of constants here. So if we factor out, let's say 4 times 3, that's going to be 12. So it's going to be 12 root 2, integral from 0 to 1. And this is going to be -2 plus 3t to the power of 3 dt. We can just evaluate this with a nice u substitution. So from here, I want you all to keep going with a u sub. So if you want to put pause on the video, go ahead and put pause on the video and then carry on those calculations. I'm going to say that you can do a u sub, where that u sub is -2 plus 3t, and you should be able to take over the rest. All right, and I will give you the answer. -15 over root 2. Sorry, -15 times root 2. All right, so that's going to be the answer to it. Now, what if we had a different but yet very, very similar question? All right, so what if we had that similar question once again? But this time, what if we reoriented our curve to be slightly different? And I'll show you what I mean. Where C is the line segment from 1 to 2 to -2, -1. So now by this statement, my line segment is actually starting up here at 1, 2, and it's traversing downward towards -2, -1. Which means my parametrization is going to be different, or so we can think of, right? So we can go through and we can parametrize once again, or we can keep this same parametrization, the one that we worked with right up here. We just need to alter our t-values. All right, so there's two ways of doing that. Now, in the interest of working with the parametrization techniques, I want to go ahead and start it all over again. So, again, this was P and this was Q, so I'm going to take now vector QP. So vector QP, again, ending minus beginning. So we're going to go to the ending. Ending is here. Ending minus beginning, that's -3. Ending minus beginning, -3. And we're starting at the point Q. Point Q is 1, 2. Which means my vector here is just going to be 1 plus this guy, so it's going to be 1 minus 3t. And then we're going to have this component, so 2 minus, or in this case plus -3t. So minus 3t, and there we are. And this is going to be for my t values. My t values here, since they begin over here, let's see what's going to happen. Alright, if t is equal to 0, then we naturally get 1, 2. If t is equal to 1, then we naturally get -2, -1, which is this point here. Nice. So we can go through and we can take the derivative, and then we can take the magnitude of that derivative, but the magnitude of that derivative is still going to give us the same value of 15, or sorry, of 3 root 2. Alright. So when we do the integration then, this integration for the curve of 4x cubed ds is now going to turn into the parametrization from 0 to 1, that's where that curve was located, for 4 times x. The x coordinate that we're choosing is this x coordinate, which is 1 minus 3t. And that's cubed. And that's still multiplied by 3 root 2 dt. If we clean this up, we should still get 12 root 2 multiplied by the integral from 0 to 1 for 1 minus 3t to the power of 3 dt. And there we have it. Now, what I want you to do is I want you to keep going. I want you to keep going, and I want you to find out what is this particular answer. Alright, so I will be looking for this answer on the discussion board. So make sure that you guys are well prepared to make sure that you answer this particular question. Awesome. So keep that in mind. All right, so let's go through and let's try a different example. We want to evaluate the line integral for xyz ds, and this is going to be where the curve C is the helix given by r of t, which is comprised of cosine of t, sine of t, and 3t. And this is going to be where t is bounded between 0 and 4 pi. Alright, now this type of problem is kind of great because they actually give us the parametrization. We don't need to go through the parametrization techniques in this particular example. All we need to do is figure out what is the derivative of the position. It's going to be negative sine t, cosine t, and 3. Then we need to find its magnitude. Alright, the magnitude, that's going to be sine squared t plus cosine squared t plus 9. That's all in the square roots, which will make it, this is 1, 9, so it's going to be square root of 10. There we are. Perfect. So that's the magnitude. Now, when I set up my line integral, so the line integral for x, y, z with respect to ds, this is now going to be the line integral for this curve, where this curve is parametrized between 0 and 4 pi. X is this component. Alright, so here's my x component, my y component, and my z component. So my x component is just cosine t, y component is sine t, z component is 3t, magnitude is root 10, and then this is going to be with respect to dt. So again, this is my x, this is my y, this is my z, and this is my derivative of r prime of t, magnitude of that derivative of r prime of t. Alright, so what does this look like now? Let's clean it up. Alright, we have root 10 multiplied by the integral from 0 to 4 pi. And this is now, actually there's a 3 in there that I can factor out. So 3 root 10, there we are. And this is going to be t times cosine t times sine t dt. Exactly like that. Perfect. Alright, so the next process is that we now need to figure out how to go about this particular piece. Alright, how are we going to go about through integrating this piece? Now, one of the things that I kind of look at here is that this piece right in here, cosine t sine t, this kind of resembles a double angle. It kind of resembles a double angle in the sense that it kind of looks like sine of 2 theta, but sine of 2 theta is 2 sine theta cosine theta, which means we're kind of missing that 2. So if I naturally multiply and divide by 2, I can get that to come out. So let's see, 3 root 10 divided by, I'm going to say 2. If I divide by 2, then I need to insert a 2 in here. So that's going to be from 0 to 4 pi t, and that's going to be 2 sine t cosine t, just like this dt. And again, 2 and divide by 2, it just means they cancel out. But now this is a double angle, and because it's a double angle, that's going to be very useful for us. That's now going to be sine of 2t dt. And from here, I do believe we can just use by parts, and by parts will actually break it off real nice here. So let's see if we can use by parts. Alright, so I'm going to say u is equal to t, since that will make this just dt. And then my dv component is going to be sine of 2t dt, which means my v component is just going to be, what's that, negative 1/2 cosine of 2t, if I'm correct. And let's see, take this derivative really quick to make sure we get down here. Taking this derivative, negative cosine, that derivative is just sine, multiplied by the derivative of the inside, that's 2 times 1/2, that's just 1. Perfect. Awesome, yeah, looks good. So by parts, I'm going to multiply here. Let's go a little bit lower. There we go. So u times v, so that's going to be t times negative 1/2 cosine 2t. Alright, so that's u times v minus the integral, and again this is still evaluated from 0 to 4 pi, minus the integral of v du. So v du, that's negative 1/2, so it's going to be negative 1/2 cosine of 2t multiplied by dt. And we should be able to grab that. Alright, so making some insertions here. Let's see, 3 root 10 over 2. Let's simplify this a little bit. This is going to be negative t over 2 cosine of 2t evaluated from 0 to 4 pi, and this is going to be plus 1/2 from 0 to 4 pi multiplied by cosine of 2t, and we can integrate there. Nice. So from here I want you guys to keep going. So if you want to put pause on the video, go ahead and put pause on the video and keep going from there. Alright, now when you keep going from there, that's going to be awesome because you're going to get a really nice answer. That really nice answer, and if you don't want the answer yet, put pause on the video because spoiler alert, here comes the answer. The answer is negative 3 root 10 pi. Now again, when you're doing this on an exam, what I'm looking for is I'm looking for the steps. I don't care that you actually get to the correct answer. The correct answer on my exams isn't worth a lot of points. it's the setup and it's the process that I'm really looking forward to. All right, so that's this type of line integral that deals with R space 3. Now, oftentimes we get these line integrals to occur, and these line integrals that we get to occur might only be with respect to one of the variables that we have. Now I'm going to put pause and I'm going to come back to make the videos later because these gardeners are out here gardening, so I'll be back in a bit. Alright, here we go. Now, some line integrals of the function can be thought of as taking them with respect to a certain variable. Now, if this is the case, then when we have a line integral over some curve C for this function f of x, y, we're not going to do this with respect to ds. Instead, we're going to do this with respect to dx, which means that we're only concerned about what our x values are doing within this function and how are they changing. Now, if this happens, then we can still parameterize using our components x of t and y of t. The only difference here is that we don't have the magnitude of that position vector. In that instance, we're only going to have the derivative of the x component in terms of t, and this is going to be with respect to dt. All right. Now, we could also have this line integral with respect to y. If that's the case, then this curve, or this line integral over this curve, is going to be with respect to y. And if this is the case, again, we're going to have some bounds. Our function's always going to be comprised of the parametrization. However, the magnitude, the derivative of the magnitude that we look at, or the magnitude of the derivative that we look at, is now just going to be the derivative of y of t, which is going to just be y prime of t dt. Now, this is just particular notation that we use, and the notation that we use is right here. This is going to signify here that we're going to take this line integral with respect to x, and we're going to take this line integral with respect to y. Oftentimes, this happens very frequently, that what we do here in this particular case is that we look at two line integrals, one with respect to x and one with respect to y, for these two separate functions over the exact same curve. If this happens, then because they're over the exact same curve, we can actually combine them into one integral that will have two different differentials. The first one's just going to be with respect to x, and the second one is going to be with respect to y. Oops, excuse me. Like such. And typically, shorthand notation for this is just the line integral for the curve of p dx plus q dy. And again, this can be extended for another component. The other component just would be the line integral with respect to z. It would look very similar, but except this would have, again, a third component. And this here would have another third component as well, when we would have this mixture of these differentials within this line integral. All right, so for this example, we want to evaluate the line integral over the curve for sine of pi y dy plus y x squared dx. And this is going to be where C is the line segment from 0, 2 over to 1, 4. Alright, so they're giving me the curve is this line segment. So the first thing that I'm going to do is I'm going to parameterize that line segment. So let's go through that process. Again, if I consider this P and this Q, so this is P and this is Q, I'm just going to take vector PQ, like such, and that's going to be ending minus beginning, so that's going to be just 1, 2. And the gardeners are back. It's alright. Starting point, 0, 2. Alright, which means my position vector here is going to be 0, 1t, comma, 2 plus 2t, like such. And we're going to make sure we parameterize this with a certain, or with certain parameters on here. So from 0 to 1, there we are. Now all we get to do is we get to go through this mixed integral here, that mixed line integral. Alright, so what I'm going to do really quickly here is I'm going to start identifying r prime of t. R prime of t, so take the derivative, that's just 1, and this in here, that's just 2. Perfect. Alright, so this line integral that we are given, the line integral over the curve for sine of pi y dy plus y x squared dx can now be thought of as this first piece here. Notice the curve is going to extend for both of them, so the curve we can actually go through independently. Alright, so what I'm going to do here is I'm going to say the curve for sine of pi y dy plus the curve for y x squared dx. Now for sine of pi y, alright, so sine of pi y dy, the curve, again, the curve is still this curve parameterized by this piece, so this goes from 0 to 1. And this is going to be sine of y. Now, what was that y component that we found? Well, that y component that we found was this piece right in here. Which means I'm going to take pi, and I'm going to multiply it by that piece, which is 2 plus 2t. dy, that's just the derivative of the y component. The derivative of the y component is 2. So that's this piece here. And that's what I'm going to multiply by. That's going to be 2, but in this case it's dt, right? If we use the differential argument. Plus, the curve once again goes from 0 to 1. The y component that we're using, again, it's that 2 plus 2t. Alright, that's for the y component. The x component we're using as just 1t. That's this piece right here. So that's just t. There we are. And that's going to be raised to the power of 2. And then we need to insert here the differential with respect to x. The differential with respect to x, that was this piece here, so that's just multiplied by 1. And then that's still dt. There we are. Perfect. So all we get to do now is we get to evaluate this integral. Now notice, did I really need to split this up like I did here? No. I could have just written this from 0 to 1 and then just use all of my individual components to say that this is 2 times sine of pi times 2 plus 2t. There we are. dt is going to factor out all the way to the end. Same integral. There we are. So that's going to be t squared multiplied by 2 plus 2t. And this would all be just dt. So did I need to split it up? No. Did we want to? It might illustrate why we do certain actions. All right. So from here, I would just want to elaborate. I just want to integrate here. So I'm going to say, hey, I want you guys to keep going. See if you can find that integral. All right. A nice U substitution should suffice here for this sine function. And then over here, nice distribution. So distribute, and then go ahead and just use a direct power rule, and everything's going to be fine. Here we get 7/6. Not too bad. Not bad at all. All right. Now, I'm going to take a step back, and I'm going to say, hey, I kind of want to use this question again. So let's go ahead and let's use that question again. So I'm going to copy that. All right, hopefully I hit copy. There we go. Now I'm going to put that down here. There we are. Now, I'm going to modify this. It's going to go from 1,4 over to 0,2. So again, now all we're doing is we're changing the direction here. All right, so this line segment now is getting reversed. So we first then need to find what is that r of t component that we use. That r of t component should get us 1 minus t and then 4 minus 2t. And this is going to be for the t values being bounded between 0 and 1. Now, how does that line integral then look? Well, the line integral for the curve C for sine of pi y dy plus yx squared dx will now be the integral from 0 to 1, and this is going to be for sine of pi times 4 minus 2t multiplied by negative 2 dt plus 4 minus 2t multiplied by 1 minus t cubed multiplied by negative 1 dt. And so this is that line integral that we then just need to evaluate. All right. And so again, I'm going to leave that work up to you all. This is great practice for evaluating these integrals. All right. On the on the right hand side over here, this rightmost term, you're probably going to have to distribute many times to figure out what that line integral is going to be. And that's okay. Make sure we get that expansion done. All right. So this answer, now notice, should we probably get the same answer? More than likely. Negative. The answer is opposite of the previous example. Why is that? Well, if we keep track of what we were integrating, one method was to integrate from one point to the curve to the other. So starting at point P, going over to point Q. But then I flipped everything around and I changed the direction. Now we went from point Q over to point P. If we do that for a line integral, and the line integral is directly with dx and dy, then it must be negative. All right. Now, this is going to be one of those important properties that we see, and this is going to say if C is any curve, then the integral over the negative version of that curve, or the negative traversing of that curve with respect to dx, is just going to be the negative version of that integral over that curve with respect to dx. This happens very similarly for the y components as well. If we do this dy, then this will just be negative integral over that curve for f of x, y, dy. All right. Now, naturally, the extension is, well, what if we then had mixed integrals? Well, if these integrals, or if these line integrals were then mixed in this particular case where we're traversing the curve in the opposite direction, then naturally the process is still going to hold like we did right up here. Just like that. Alright, so again, we get this natural progression that we want for these curves as we start moving through these line integrals. So far we have two types of different line integrals. One line integral is line integral with respect to a certain variable, and that's our dx or dy or dz. The second type of line integral that we have is when we take the line integral with respect to its arc length. When it's respect to its arc length, that's just going to be our integral with respect to ds. Alright, so it doesn't look too bad at this point in time, and again, hopefully it doesn't get that bad. Alright, now, one of the last items that I want to focus on here. Is that I want to create this vector field. So I'm going to say let f of xyz be a vector field. Where f of xyz is going to be defined as some p function that has possibly 3 components, some q function that has, again, possibly 3 variables, and some r function that, again, possibly has 3 different variables. Alright, there we go. And, so a vector field where this happens. Alright, good. And r of t is going to be some x of t in the I component, some y of t in the j component, and some z of t in the k component for t bounded between a and b. And I'm going to say that r of t is a smooth curve. Alright, so what I want to do at this point in time is, now that I have these definitions for this particular case, that I have this vector field and I also have this smooth curve taking place, what I want to do now is I want to start looking at this vector, and more specifically this vector field with respect to its parametrization of the curve. Now, when I start looking at this, I'm going to say this is going to be my curve. I'm going to do a line integral with respect to my curve, line integral of my curve over this vector field, and I'm going to do this with respect to its curve. Alright, and that's a curve that we defined as a vector position function. Now, in order to do this, well, one of the things that I'm going to have to do is I'm going to need to find a direction for the curve. Because again, we always want to make sure we orient the curve accordingly. Because orientation, when we do this with respect to dx or dy, it's going to matter. If we do it with respect to ds, meaning the arc length, then it doesn't matter our orientation. We can go whichever way we'd like. But since we're going to do this with respect to the position function, and we don't know if we're going to have dx or dy, we're just going to do it in general. So I want you to then recall what value or what process gets us a direction that is traveled on a curve if we have a vector position function. I'm going to write that answer here. The unit tangent vector. The unit tangent vector gets you the direction that you're traversing along the curve. Therefore, if we then start looking at the vector field and we dot that with the direction, then we'll automatically be able to take this with respect to s, its arc length. Now, when we're still working with this, what I'm going to do is I'm going to take my function in this vector field. Taking this vector field function, I'm going to parameterize this vector field function with respect to this curve. So notice I'm doing a function composition. This is my x component, this is my y component, this is my z component, and I'm going to make all of those compositions into my vector field function. But when I do this, I always have to account for that chain rule that's going to take place, and I'll get there in just a little bit. But now my vector, unit tangent vector. The unit tangent vector, if you remember, that's just a derivative of the position divided by its magnitude. But ds, according to the previous work that we did, ds is just the magnitude of r prime of t dt. So this actually turns out real nice that if I make my parameterizations for my curve and I embed that curve in some vector field, then by performing this function composition of my vector position function with my vector field components, these naturally should cancel out, which means I should just get r prime of t dt. And this is what I want to look at. This is one of the definitions, or this is one of the values that we work with when we're talking about line integrals. More specifically, when these line integrals are moving through a vector field. All right. Now, what does that look like? Well, let's go on to GeoGebra. All right, so we're back here on GeoGebra, and I'm going to go down here to this vector field example. I'm going to click on that. There we are. So again, what I did here is I took this vector field, and that's all of these arrows. Notice all the arrows are not a unit 1 vector. All right, so it makes it look a little bit more convoluted. Now, I've also taken this curve and I've embedded it in this vector field, and I've parameterized the curve here. You can change the different parameters to see what you will then get, and you can also change the different functions here for your vector field. Again, this is only a vector field in RSpace 2, so just keep that in mind. Now, watch what's going to happen as I start moving an object through this vector field. The blue vector is a unit tangent vector that I just talked about, moving along that parameterization for the curve. I want you to notice that red vector. That red vector shows the direction of the curve at the given point that's on the curve. So notice it, as the vector keeps going, let's say if we stop it, this vector here, the red vector, kind of looks very similar to these other vectors that are happening around it on that vector field. Which again, it's just an interpretation of what happens when this object is moving along that specific object, that object is moving along that specific curve inside of that vector field. That's what the line integral is doing when we're looking at a line integral moving along a curve inside of a vector field. All right, so this works the same for RSpace 3. If we were able to create a curve in RSpace 3, which we can do, and if we can create a vector field in RSpace 3, which we can do, then we can naturally traverse an object on that curve inside of that field, and we can then calculate that line integral. So let's go back. Here we are. All right, so naturally we want to look at one of these examples. So let's start looking at one of these examples. We want to evaluate the line integral for this vector field with respect to r here, where my vector field function is 8x squared yz in the I component plus 5z in the j component minus 4xy in the k component, and c is the curve given by r of t, which is t in the I component, plus t squared in the j component, plus t cubed in the k component. Alright, there we go. And this is going to be for t is bounded between 0 and 1. Nice. Alright, so there's a few things that we need to do. In order to be able to do this, what we're going to need here is we're going to look at this function. That's what's actually being given to us. That's what they want us to evaluate. And we want to make sure that we arrive at this conclusion here that says that we are able to evaluate this line integral for this specific curve as it's moving through this vector field. All right, so the first thing, or one of the first things that I want to do is I want to calculate a derivative. All right, that's going to be one of the first things that we take here. So let's calculate that derivative. I'm going to put this in a vector form here, so that's going to be 1. All right, that's going to be 2t, and that's going to be 3t squared. Nice. All right, good so far. Now, next piece of information. I'm going to need to compose my vector field, function composition here of the vector field, with my vector position function. So the vector position function, I'm going to grab this as x is equal to t from here, y is equal to t squared, and then z is equal to t cubed. Given this, what I'm going to do now is I'm going to compose my vector field function. So this is going to be 8 times x, where x is just t, and that's squared, times y, and then times z. Y, that was that t squared. Z was that t cubed. Nice. So far so good. And this is all in the I component, plus 5 times z, where z is that t cubed. All right, and that's in the j component, minus 4 times x times y, and that's going to be in the k component. All right, so that's x and y, so that's going to be t times t squared. Perfect. So let's clean this up a bit. All right, so this is going to be 8 multiplied by, let's see, that's t squared, and t cubed. So it's going to be t to the 7th, and that's in the I component, plus, you know what? I actually want to rewrite this differently. I want to take it out of the unit basis vectors, and I want to just do it with vector component form. So this is going to be 8t to the 7th. The next one's going to be, here we are. So on here, I see 5, and then z. Z was, here we are, t cubed. So that will naturally, all right, perfect. Just be 5 t cubed. Nice. And then the next one, that's going to be 4, or in this case, negative 4 t cubed. All right, it's looking pretty good so far. All right, not too bad. So that's 8t to the 7th plus 5t cubed minus 4t cubed. Awesome. Perfect so far. Now, once we have this piece, that's this guy that we just found, and we just found this derivative as well, what we want to do is we want to take the dot product of those two. So let's go ahead now and let's take the dot product of the two. So we're going to take the dot product of this function composition for these vectors and the derivative of r prime of t. So that dot product, 8t to the 7th, 5t cubed, negative 4t cubed, and we're going to dot this with 1, 2, and 3t squared. This should naturally get us 8t to the 7th plus, we're going to multiply here, 10t to the 3rd. All right, it's looking good. Oh, did I miss something here? Sorry, I forgot that 2t. My apologies, I forgot that 2t, which makes this t to the 4th. Uh-oh. ¿Qué pasó? My apologies there, everybody. I have no idea what happened. It just kicked me out. That's rough. But luckily, the work was saved, and we're going to see if the work was saved. I'm kind of nervous. Ooh, it's looking good so far. Yay! Alright, here we go. Alright, and again, I said that I had made a mistake here. So this was really to t to the fourth. There we go, 10t to the fourth. And then minus negative and 3, so it's going to be 12t to the fifth. There we are. So when we try to calculate this line integral for the curve of f dot dr now becomes the line integral over the curve of the function composition with respect to r of t. And that's going to be dot r prime of t dt, which now means I'm integrating the curve, so that's from 0 to 1. This integrand is now this function that I'm integrating, which is 8t to the 7th plus 10t to the 4th minus 12t to the 5th. And this is all r prime of t, or sorry, r prime was already taken care of, and that's just dt. So it turns out into a really, really nice, straightforward integral once everything is said and done. And this here would then get us, if you keep going, Big Master 1. That's our answer. Just 1. And there you have it. That is the whole process for line integrals. Alright, so I hope you guys enjoyed this process for line integrals, and next time we're going to be getting more into these line integrals as to how we look at them, how we evaluate them when they're going into more specific vector fields, meaning are they conservative vector fields or are they not? If they are, then we can, work with some stuff. So, I hope you guys enjoyed it, and I'll see you all next time.